Hey there everyone, welcome back. We are moving on with our lessons on systems of equations, and last lesson we learned how to solve these systems of equations by graphing them. We're going to keep that skill in our back pockets because we'll need it still, but we're going to learn another way to solve these, which is algebraically. And we're going to learn two different ways of solving these systems algebraically. The first is substitution, and the second is elimination, and really they're just different versions of the same thing, which is just algebraic tricks really in order to get us to our solutions. So remember that when we have a system of equations, so we have two or more equations, as long as we have the same number of equations as we have variables, then we can actually solve to see what our solutions are. And if we have linear quadratic or quadratic systems, then we can have multiple possible solutions. We might have two, we might have one, or we might have zero, just depending on how they all line up. So the first method we're going to use here is something called substitution. And I'll just sort of summarize the rules that we're going to follow on the side here. So if I have a system of equations, I can isolate one of the variables in one of my equations. And then I can substitute that into the second equation so that it eliminates that variable. And then I'll have just one variable that I'll have to work with. And I can go through. And of course, at the very end, we're going to verify our answers. So what does this look like? Well, the first thing we need to do is we need to isolate one of our variables in one of our equations. So I'm going to pick the simplest of these two equations, which is 5x minus y equal to 10, and I'm going to solve that for y. I'm going to isolate it so that y is on its own. You can see that I could move this y to the other side of the equation. I could move that 10 to the other side. I'm going to kind of skip a few steps here, but maybe you could do this in your head and say y is going to be equal to 5x minus 10. So that's the same equation as the first one. If y is equal to 5x minus 10, then what I can do is in this second equation, I'm going to substitute anywhere I see y, I can actually put in 5x minus 10. So I'm just going to actually put this into this equation anywhere that I see y. And what's going to happen to this equation is it can now be written as x squared plus x, that doesn't change, but then minus 2 times 5x minus 10 equals 0. And this is still the same equation because remember y is equal to 5x minus 10. If I go ahead, I should just stop and look at this and say, hey look, I recognize now that I've only got x's to deal with, and so there should be a way to solve this. So I'm just going to expand through my brackets here. I'm going to expand along there, and I get x squared plus x minus 10x plus 20 equals 0. And then I'm going to collect my like terms. So I get x squared minus 9x plus 20 equals 0. And so this is something that I could solve. It's all set up for me. Maybe I can factor it. So what are two numbers that are going to add up to negative 9 that would multiply to be 20? And so positive 20 will have the same sign. That's going to be negative. It'll be negative 4 and negative 5 are my two factors. And so I have x minus 4 times x minus 5 equals 0. And then going through the final steps here of solving, I can see that x is going to equal 4 or 5. So I've got my solutions for my 2 points. It looks like I've got a line crossing a parabola, so no surprise I've got 2 points there. Don't forget though that you're not done. A full solution is going to include the ordered pair. So there's two possibilities. So for example, when x equals 4, let's think about what this means. I'm gonna substitute this back in here and figure out what y would be. Well, y is going to equal 5 times 4 minus 10, which would be 20 minus 10, which is 10. So one of my ordered pairs, one of my solutions would be 4, 10. I can do that same thing to see what happens when x equals 5. So when x equals 5, then y is going to equal 5 times 5 minus 10 is 15. So my second solution is going to be 5, 15. And so these are my two solutions. 4, 10 and 5, 15 are my two solutions. What I should do though is I really should verify this because I want to make sure that this is going to work. So I plugged these numbers, I plugged x equal to 4 and x equal to 5. I plug those back into my first equation. What I'm going to do then is I'm going to use my second equation to verify, and I'm going to see if this works. So I'm going to plug this ordered pair. Let's just test out 4, 10. Let's test that out. And I'm going to put this into my second equation and see what I get. So I've got 4 squared plus 4 minus 2 times 10. Does that equal 0? And so I have 16 plus 4 minus 20 equal to 0. And I can see, yeah, that works. So that is correct. So that answer has been verified. And then I'm going to do the same thing here for my next solution set. So let's just verify 5, 15. And so I've got 5 squared plus 5 minus 2 times 15. Is that equal to 0? And of course I have 25 plus 5 minus 30 equals 0. And yes, you can see that this has also been verified. So I know these are my two solutions. So that's substitution using a linear quadratic system. And so you can see here, one thing to take away from this is that it was a lot easier for me to solve for y. So in many cases, that's going to be the case. Let's take a look at a quadratic system like we have here. One way to do it, I could do it like I did the last one, but I'm going to do this one just a little bit differently because sometimes students like a slightly different method. I've got some more complicated equations here. And what I'm going to do is I'm going to solve both of them in terms of y. So I'm going to isolate y for both of these equations and just see what I get. So this first equation here, I can see that if I just kick y over to the other side of the equation, I could write this as y is equal to 3x squared minus x minus 2. And if I do the same thing in this case here, I'm going to kick this y over to the other side there, and then I'm going to bring this 4 over to the other side. I can see that this turns into y is equal to 6x squared plus 4x minus 4. And so for my substitution, I can see that if y equals 3x squared minus x minus 2, and y also equals 6x squared plus 4x minus 4, then these two things here must also be equal to each other. So I could rewrite this, this equation as just 3x squared minus x minus 2 is equal to 6x squared plus 4x minus 4. And so again, I see that I'm in a situation where I've only got x's that I'm gonna have to deal with. I've got some algebra to do, I gotta move some stuff around, but that's not too bad. I'm gonna bring 3x over to the other side here and collect like terms. I'm gonna add x to both sides to bring that over, and then I'm gonna add 2 to both sides to bring that over. And I'd end up with 0 is equal to 6x squared minus 3x squared is 3x squared. And then I had to add x over here, so I get plus 5x. And then I've got to add 2 to both sides here, so I get minus 2. And so I could solve this any way you like, I guess graphing or factoring or quadratic formula. Now that I take a quick look at this, I can see here that I think we're going to be able to do this by decomposition. So I'm going to try that first. It's always nice to try and factor first. Remember that if we're going to do decomposition, we do this when our a value is not equal to 1. So I'm going to remember to multiply this 3 times negative 2. So I'm looking for two numbers that add up to 5, but then when I multiply them, I don't just look at the c value, it's got to be 3 times minus 2. They're going to multiply to negative 6. And so the two numbers that are going to give me this result are going to be positive 6 and negative 1. So 6 and negative 1. And so I'm going to decompose this second term. I still have 0 equal to 3x squared. I'm going to decompose the second term into plus 6x and then minus x and then minus 2. And then I'm going to factor out whatever I can. So I have 0 equals 3x, and then I have x plus 2, and I'll factor out a minus 1, and I get x plus 2. And then this ends up being 0 is equal to 3x minus 1 times x plus 2. And of course, then just to finish it off, I'm going to solve for x, and so I can see that x in this case can equal minus 2, and it can equal positive 1/3. So those are my two solutions for x. I'm not finished, of course, because I have to then find the ordered pair. I know what x is, but I have to find what y would be in each of those cases. So I'm going to go over here and I'm going to say, okay, what will y equal when x is equal to -2? Now, it doesn't really matter which equation you choose to substitute it into. In the last example, one of them was linear, and so it was a lot easier. In this case, they're both quadratic, so I'm not sure it really matters. So I'll just substitute it into the first one. So I get y is equal to 3 times -2 squared minus -2 minus 2. And so I have to be really careful with my negative signs here. -2 squared is 4 times 3 is going to give me positive 12. And then minus -2 would give me plus 2 and then minus 2. So I guess my y value would be 12. And so my first solution here, my ordered pair, would be -2 and positive 12. I'll do this again now for x equal to 1/3. And so I would get y is equal to 3 times 1/3 squared minus 1/3 minus 2. And so if I'm careful here, 1/3 squared is 1/9, but then times 3 is actually just 1/3. So this becomes 1/3 minus 1/3 minus 2, which is just minus 2. And so my second ordered pair is going to be 1/3 comma minus 2. And so these are my two solutions. Now, I'm not quite done because I really should verify this, but I'm going to be honest with you. Taking both of these and then substituting them into the second quadratic and then cranking those through and seeing if those give me the right answer, I could do that, and you're welcome to do that. I'm not going to do that because I'm feeling too lazy. So instead, another way to verify these things is to rely on our graphing. So I could jump over to my graphing calculator. You can see here that I punched in these two equations, and I can take a look and see where these two graphs intersect, and I can note these 2 points. They happen at the point -212 and the point 0.333 or 1/3 and -2, which are the two answers that I got when I solved it. So I can solve it graphically, or sorry, I can verify it graphically, and that was a lot quicker, and I like that a lot better. So that's actually just the first way of solving these systems, and that's called substitution. A slightly different method, which is just another algebraic way of going around it, but sometimes is going to make your life a little bit easier, is something called elimination. And so I'm going to solve the exact same two systems as we saw before, but I'm just going to now solve them using the elimination system. And so in the elimination system, or strategy, if you will, we're going to follow these steps right here. So the first thing we're going to do is we're going to align our two equations so that the same variables with the same degrees are kind of in a line. So you can see here that I've lined up my 5x and my x, I've lined up my y and my y, and I haven't lined up anything with x squared because there isn't another term in that other equation. And once I've done that, this is the trick, is we're then going to multiply or divide, or usually multiply one of the equations so that one of the variables will be eliminated, and that's usually the y variable. And then after we do that, we're just going to add the two equations together or subtract the two equations, and that will solve it for us. So what I'm going to notice here is that if I added any of these two, like if I added these x's or those y's, they wouldn't cancel out. But I can do whatever I want to these two equations as long as I do the same thing to the whole equation. And so, for example, what I might do is I'm going to multiply this whole equation by -2. Just the whole thing by -2. And so this first equation stays the same. It's still, or sorry, the second equation. So this is still x squared plus x minus 2y equals 0. But when I multiply this second equation by -2, I get minus 10x, and then I get plus 2y, and then I get equals -20. And so why did I choose -2? Well, I chose -2 because if you look closely here, now this term right here, if I add those two terms together, they're going to cancel out. And so I can actually do this. I can add the entire equations. I can add one equation to another because again, it's an equation. I add the left side of both equations together and I add the right side of both equations together. And because they're an equation, that's still going to be a valid equation at the end. So x squared plus 0 is still just x squared. 1x plus negative 10x is going to be negative 9x. And then negative 2y plus 2y is just going to be 0. And then I get 0 plus negative 20 is negative 20. And so you can see this familiar equation kind of come back again. We saw that before. This can just be written as x squared minus 9x, and I'll bring that 20 over to the other side of the equation, so I'll go plus 20 equals 0. And now we're going to kind of go down the same path again. I won't go through all the steps, but you can see that this will then factor out to x minus 4, x minus 5 equals 0, and so x is going to equal 4 and 5. And I'm going to stop there because we already know what will happen. We can find the two y values and then verify both those ordered pairs either by substituting back into the equation or by graphing, either way. But we can see that we kind of end up in the same spot. So let's try this same strategy here for our quadratic system. And the thing to keep in mind here is you're usually gonna want to eliminate the y variable. And the reason is because the odds that both the x and the x squared term will eliminate are really, really low. It happens sometimes in some systems, but you wouldn't expect it to normally. And so it's difficult to try and get those things to eliminate. Now you can see here that when I line these are already lined up for me. But if I were to add these two equations together, they wouldn't eliminate. Even though this y, negative y, and this y, negative y, even though they have the same coefficients, negative y plus negative y, well, that's just going to be negative 2y, and that's not going to get me where I need to go. So instead of adding these two equations together, what I'm going to do is I'm going to subtract this whole equation from the first one. So I'm going to do the first equation minus the second one, and I'm going to see what happens. So 3x squared minus 6x squared is negative 3x squared. Negative x minus 4x is minus 5x. Negative y minus negative y is 0. And then negative 2 minus 0 is negative 2. And then over here, I've got 0 minus 4 is minus 4. And so if I collect the terms and bring everything over to the same side of the equation, I'm going to get negative 3x squared minus 5x. And then if I bring this negative 4 over here by adding 4 to both sides, I would get plus 2 and then equals 0. Now this might look similar, might look familiar, but I've got this negative term here, and so I don't really like that negative term. I don't like it when a is negative. It doesn't really matter, but it bothers me, and so I'm just going to eliminate that by multiplying everything by negative 1. And now this equation becomes 3x squared plus 5x minus 2 equals 0, and this is the exact same equation that we had before. We can decompose this down into 3x squared plus 6x minus x minus 2 equals 0, and then we can factor out 3x, x plus 2 minus 1, x plus 2 equals 0, and we're back to 3x minus 1 times x plus 2 equals 0, and we're right back to where we were in the last example, where x can equal negative 2 and positive 1/3. So again, I'm not going to go through the rest of that solution because it would be just identical. We'd have to go and find our y values, take those ordered pairs, and then verify them somehow. I suggest graphing because it's going to be a lot simpler. Okay, so that's the two methods we've got for solving algebraically.